Hello, and welcome back to our final set of lectures for our statistics lecture series for ENIGMA-U. In the past, we've been talking about how to figure out whether or not the means of two samples or populations or a sample to a population are the same, and whether or not that shows a treatment effect. But today, we're going to talk about how to use statistics to analyze the correlation or lack thereof between two variables, which is honestly, oops, excuse me, what a lot of you will probably be using statistics for in your own research studies. So today, here are the symbols, formulas, and concepts that we're going to be talking about, but I'm just going to hop right into it. So correlation. Correlation is different from anything we've talked about so far. It is a hypothesis testing procedure that we use to measure and describe the relationship between two variables. It involves the observation of two variables as they exist naturally. We're not manipulating any conditions. We're not creating treatment conditions or anything like that. We are merely observing and seeing if a pre-existing relationship exists between two variables. And what we mean by a relationship is when changes in one variable, x, tend to be accompanied by consistent and predictable changes in another variable, y. Here's an example of correlation. So if our research question was, is there a relationship between family income and students' average grades? What we're going to do is we're going to take a sample of families, collect their income, and then collect the final grades of the students in that family. What you see here is we're not manipulating anything. We're not changing family income. We're not changing grades. All we're doing is deciding those two variables and then measuring them and comparing them to each other. But if what we see here is that there's only one group of scores, average grades, that's what we would maybe say is a dependent variable. Evaluating the mean of this, we have nothing to compare it to. It won't tell us anything about the relationship between income and grades. So we're going to instead plot it on a graph here. And now we're evaluating the relationship between family income and average grades. And we can see that relationship represented by this line here. So correlation describes three characteristics of a relationship between two variables. One is the direction of the relationship. Two is the form that the relationship takes. And three is the strength of that relationship. So direction. So a correlation describes direction. So we can have two directions of our correlations. One is we can have a positive relationship or a negative relationship. A positive relationship is when the two variables change in the same direction. They either both increase or both decrease, but either way they're changing together. A relationship or an example of that is income and weight for men. So as we can see here, as income increases for men, weight also increases. We see that that's that relationship. A correlation could also describe a negative relationship, which is when the two variables go in opposite directions. When one increases, the other decreases, or vice versa. An example of that is income and weight for women. As income for women increases, their weight decreases. And I'm not talking about that in terms of one woman changing her weight and her income changes. This is just the relationship we see between taking lots of women, the income of lots of women, and their corresponding weights. We'll get into that in a little bit, why when we're talking about direction, there's no causality there. Correlation also describes form, and there are lots of different forms that a relationship can take, but they all fall into one of these two categories. One is a linear relationship. So one variable is going to change by approximately the same rate as the other variable increases by 1 unit. So what we can see here is as GPA increases by 1 unit from 2 to 3 and 3 to 4, the change in motivation is pretty consistent. That gives us that straight line or linear line. You can also have a curvilinear relationship, which is when one variable does not change at a constant rate and sometimes even changes directions. And we can see that here. It is curving and not changing at the same rate. Our working memory is curving like this as age just keeps going by 1 unit. Correlation can also describe strength. And the strength of the relationship is demonstrated by the slope of the line in the relationship that we're looking at. So these are just some examples of different strengths. A perfect negative correlation has that perfect diagonal downward slope. That's the strongest negative correlation you can have. No correlation is going to look like this. The slope is just a straight line or zero. There's no correlation between whatever these two variables are. This is a strong positive correlation because as we can see, it's going up, so it's positive. As one variable increases, so does the other. But it's not a perfect positive correlation. If it were, the line would look more like this, a perfect diagonal. And this is a negative correlation, but a weak negative correlation. The slope is closer to zero than it is to this perfect correlation here. So now that we know what sorts of things correlation can describe or what sorts of things correlation can tell us, let's figure out how we actually calculate it. We calculate correlation using something called Pearson's correlation or Pearson's R. It's also called the Pearson moment or product moment correlation. Basically what this is, it's a measure of the direction and the strength of a linear relationship between two variables. We can only use Pearson's R when we have a linear relationship. That'll be important later. And what Pearson's R does is it forms a ratio. It's a ratio that compares the degree to which X and Y vary together, which we figure out by the sum of the products, compared to the degree to which X and Y, just two variables, vary separately, which we find out by computing the sum of the squares for the scores of each variable. And I'll show you how to do that in a second. Basically, what we're trying to do with Pearson's R is trying to determine if changes in one variable are accompanied by a corresponding change in another variable. So let's just talk a little bit about how we use Pearson's R, how we interpret Pearson's R. Pearson's R tells us about the strength and direction of a linear relationship. Remember that. The magnitude of Pearson's correlation ranges from 0 to plus or minus 1. This is going to tell us the strength. A correlation of 0 is a weak non-relationship, whereas a correlation of positive or negative 1 is a perfect correlation. The strength is max. And then the correlation can either be positive or negative depending on the direction of relationship. If you have a positive Pearson's correlation, it's going to be a positive correlation. If you have a negative Pearson's correlation, then it's going to be a negative relationship. Some examples of this are here. This obviously has no linear relationship. There's no pattern to the way that these dots are forming, these points. So what we say is Pearson's R is going to be 0. The degree to which X and Y vary together is 0 and different from the degree to which they vary separately. A perfect positive linear relationship is going to be represented by positive 1. So the degree to which X and Y vary together is the same as the degree to which X and Y vary separately because they're always changing together positively. And then a perfect negative linear relationship is going to be represented by a negative 1. The degree to which X and Y vary together is the same, but it's opposite to the degree to which they vary separately because as X goes up, Y goes down in the exact perfect relationship there. Now let's talk about how we are going to be testing our hypotheses using Pearson's R. How do we actually apply this to our statistical analyses of our science? So obviously, the first thing that we do with every hypothesis testing situation is we state our hypotheses. So here's how we state hypotheses with Pearson's correlation. As a reminder, correlation is an evaluation of the relationship between two continuous variables collected from one sample. Just like in the other hypothesis tests we've learned, you can either have a two-tailed or a one-tailed hypothesis. And in all of these cases, the null hypothesis is going to state that there's no correlation between the variables. The population correlation is going to be 0. As a note, population correlation, the correlation of those variables across the population is represented by the Greek letter rho. That's what this is right here. Whether it's a one-tailed or two-tailed, this is how we're going to represent it. The alternative hypothesis says that there's a real non-zero correlation between the two variables. A two-tailed relationship just says that Pearson's correlation is not zero. A one-tailed positive says that Pearson's correlation is going to be more than zero, and the negative says the correlation value is going to be less than zero. So the next thing we have to do when we're doing hypothesis testing is to calculate the degrees of freedom and determine the critical value. We always have to do this. This table B6 is in the textbook that these courses are from, and I will go back at the end and just show you what that textbook looks like in case you want to look it up. But you could just look up critical values for Pearson's R on Google, and you would probably get it. So the degrees of freedom in the example we're going to use on the next slide is 4. So that's why this number is 4 here. But the formula that we're going to use for Pearson's R is your degrees of freedom is n minus 2, not minus 1, because you have two variables that introduce error. That's a good way to remember that. And then here is what the critical values table looks like for Pearson's correlation. And in order to be okay, pause here for a second. Two variables can have a correlation, but they can also not be significant. Correlation and significance are mutually exclusive. You can have two variables that are significant and have correlation with each other, or you can have two variables that have correlation and are not significant, or you can have two variables that don't have any correlation and are not significant. So that's why this note is here. To be significant, the sample correlation R needs to be greater than or equal to the critical value that you get in this table. And we'll look more at that later. That was kind of confusing, but I'll show you an example of this later. Since our degrees of freedom in our example that you'll see on the next slide is 2, that's what we're going to do. We've set our alpha level to a two-tailed test of 0.05, which means that our alpha, or our p-value essentially, is going to be our critical value is going to be 0.950. Remember that number for later. So let's figure out how we calculate Pearson's R. So like we said, in the numerator here, we have the sum of the products, and in the denominator, we have the square root of the sum of the squares of each of the variables. So here's our steps when we're calculating Pearson's R. First, we need to create a scatter plot, and we'll talk about why we need to do that in a second. Second is we're going to calculate the degree to which x and y vary together, which is going to be the sum of the products of the deviations. The third step is we're going to calculate the degree to which x and y vary separately, which is our denominator here. And then using all that information, we can calculate Pearson's R. Really quickly, before we jump into this, in the past, we've used the sum of the squared deviations of each score from the mean. And that's when we take each of the deviations from the mean and we add them together. The sum of the products of deviations of each pair of scores from the mean is a little bit different than what we've used in the past. And that is actually this. So we're going to take the deviation of each pair of scores from the mean of its own variable, and then we're going to multiply them together. And I'll show you what that looks like in a second. But this is just to remind you that the sum of the products of deviations is different than the sum of the squared deviations that we've been using in the past. So the first step is to create a scatter plot. You can do this in Excel. That's probably the easiest way. I won't show you how to do that now, but hopefully some of the other courses on ENIGMA-U will touch on that a little bit more. You're going to take your scores here. This is just our sample data. We have scores for X scores from 1, 2, 3, and 4, and we have their corresponding Ys, and you can see them on this scatter plot. For example, one of our pairs of scores is X1, Y3. We have an X of 1 and a Y of 3. Once you've plotted them all, you can fit it to a linear regression line is what this is called, and it just shows the best fit of a line that will represent all 4 of these points best. The reason we do this is because Pearson's R can only be used to calculate the correlation of linear relationships. So even though there's a very clear curvilinear relationship between age and working memory, your Pearson's R would still come out to be 0 because it's not linear. So the reason that we make a scatter plot before running a Pearson's correlation analysis is to figure out if that is actually going to be appropriate for the data that you have. If you form a scatter plot and it's very clearly curvilinear, not linear, then you're not going to use Pearson's R. However, our data is linear enough that Pearson's R should work. The second step after we formed a scatter plot and figured out like this is okay, we can use Pearson's R, is we're going to calculate the numerator or sum of the products of deviations from the mean. So how we're going to do this is we calculate the mean of all of the X scores and the mean of all of the Y scores first. So the mean of all of these scores is 2.5. The mean of all the Ys is 5. Then you're going to calculate the deviations of each X score from the mean of the X's and each Y score from the mean of the Ys. So for example, our X score is 1, the mean is 2.5. We go 1 minus 2.5 gives us negative 1.5. And vice versa, our Y score is 3, the mean of the Ys is 5. We find the deviation between them, negative 2. After you've done this for all of your values, you're going to find the product of each X and Y deviation score according to the pairs of scores that were presented at the beginning. So since our original pair was X1, Y3, we're going to take the deviation of X and the deviation of Y for that pair, and we're going to multiply them to get our product of deviations. Once you have all of your products for all your pairs of scores, you're going to add them all together and get your numerator, the SP, which for this, in this instance, is a positive 2. After we've done that, we're going to calculate the denominator, so the sum of the squares. In this instance, instead of adding the products of the deviation scores together, we're going to go back to the deviation column and add those together first and then multiply them. I'll show you what we're doing. First step is you're going to find the sum of squared deviations for X and the sum of squared deviations for Y, which we are very familiar with how to do that, right? We've done that in every single every single hypothesis testing we've done thus far. Then we are going to multiply the sum of the squares for X times the sum of the squares for Y and find the square root. The sum of the squared deviations, remember, is you're going to take the deviation and then you're going to square it. You're going to take the deviation and then you're going to square it. That's what these first two steps are. And then you find the sum of all of those squared deviations, right? So the sum of the squared deviations for each variable is what we multiply. So 5 times 10, and then we take the square root of that to find our denominator. Once we have that, we can calculate Pearson's R. So if we plug both of those values into there, we get a Pearson's R of positive 0.28. And what this is, it's a weak positive correlation between X and Y. And whenever you get this number, it's important to go back to your scatter plot and say, does that number fit the slope of whatever linear line we've created? This, even at the very beginning, we could have predicted that this is a weak positive correlation just based on what that line looks like. And that's exactly what our data is telling us. Okay, then with that, we're going to make a decision. We've already decided that there's a weak positive correlation, but now we need to decide if that correlation is significant or not. Remember at the beginning, maybe I shouldn't go back, but I'm going to. We talked about how our critical value is 0.95 with a two-tailed alpha of 0.05. Now, since positive 28 is less than our critical value, 0.95, we're going to fail to reject the null hypothesis and say that there is a non-significant weak positive relationship between X and Y. And this is what I was talking about before, where you can have a relationship that is correlated. There is a weak positive relationship, but it's not significant. So correlation and significance are not mutually exclusive. Okay, are not mutually exclusive. And anyways, here's how we report our results in APA style. So in our results section here, we say using a Pearson's R correlation, two-tailed, a weak positive correlation, we say what the correlation was found between variable X and variable Y, and you would actually write the variables down in there. You wouldn't just use the letters. However, the relationship was not significant. And then we give our sample size, what our Pearson's R value was, and then we say that what our alpha level was essentially, and that our P was not less than that value. You can also report it in a table. The idea with this table, it's called a Pearson's R correlation coefficient matrix. And these are 4 different values, 4 different variables, well, income, education, age, and IQ. And the idea here is that we ran a Pearson's correlation test for each of the pairs of variables. So we ran a Pearson's R for income versus education, income versus age, income versus IQ, education versus age, education versus IQ, and age versus IQ. And we figured out which of them were significant and which of them had relationships. Generally, this key down here is for telling us the significance values. So here we can see that between income and education, there was a medium to moderate positive correlation between them, but it was also statistically significant when using an alpha of 0.01. Here we can see that between age and income, there was also a small to moderate positive correlation, and it was only significant using an alpha of 0.05. Their relationship was only significant. Here we can see that between income and IQ, there's a weak positive correlation, but it was not significant because there's no asterisks. Okay. And lastly, here are the assumptions that we make when we use Pearson's R. So we're assuming that we're using exactly 2 variables that are both measured on an interval or ratio scale, that we use random sampling, as always, that are the population distributions from which the sample was drawn must be normal, And lastly, that there's linearity, which means that each variable varies equally, no matter the magnitude of the other variable. Because remember, Pearson's R can't evaluate curvilinear relationships, only linear. We're going to stop here, and then in our next and final lecture, we're going to talk about some of the things that we can use Pearson's R to evaluate and how we can interpret our correlation values.